Okay, so in this video we're going to be recording solutions to the 2021 VCAA Exam 2. So this is a 2-hour exam paper where we can use technology, so a CAS calculator of some form. I have my TI Nspire set up here to be used. You can also access a bound reference of notes throughout the examination. And it's in 2 sections, 20 multiple choice questions and 5 extended answer questions. So let's get started. Period of the function with the rule. Okay, so this is a fairly standard early multiple choice question. Period of a trig function. It's a tan period, so you need to be a bit careful. Remember, period for a tan graph is pi on n. And so n in this case is pi on 2. So we have pi divided by n, which is pi on 2. And so that's pi times 2 on pi. And so the period here is 2. So option B. The graph of y equals log e of x plus log e of 2x, where x is bigger than 0, is identical over the same domain to the graph of... Okay, so this is just a log laws question. So these are all a single log, whereas this is 2 logs being added together. So let's combine these together. We know when we're adding 2 logs, we can combine them together by multiplying the things inside the logs. And so therefore this is the same as log e of 2x squared, which is option C. Question 3. A box contains many coloured glass beads. A random sample of 48 beads is selected, and it's found that the proportion of blue coloured beads in this sample is 0.125. Based on this sample, a 95% confidence interval for the proportion of blue coloured glass beads is... Okay, so we can use our CAS to find a confidence interval, and it's going to require the number of successes. So what we've been given here is we've been given n, which is 48, so that's the size of the sample, and we've been given p hat, which is the proportion of blue coloured beads in the sample. And so what we'll need actually to put into the CAS is not p hat, but x, the number of blue beads in the sample. So I'm just going to do 48 times 0.125. Sorry, I keep writing that incorrectly. 0.125. Okay, so that's 6. So that means there's 6 blue beads in that sample. Sorry, I can't write today. 6 blue beads in the sample. And so therefore when we do the confidence interval with the CAS, so menu 6, 6, 5 for confidence intervals, the number of successes is 6. And the n value, the size of the sample, is 48, and we want a 95% confidence interval, so we'll leave the confidence level at 0.95. And then we're looking at that C lower and C upper, so confidence lower and confidence upper, so that's the limits of our interval, and so we've got 0.0314 and 0.2186, which is option A. Okay, question 4. The maximum value of the function is blah blah blah. Okay, so it's just a simple max. You could define the function. You could use a graph. You could solve derivative equal to 0. You could use function max. So lots of options with your CAS as to how you would go about doing this. So I'm just going to define it. So whatever method I decide to use is quick and easy. I'll have to type the function in at some point anyway, so I may as well type it in here. Okay, so there's h of x. So obviously I could either solve the derivative of that equal to 0, equal to 0 for x. So that happens when x equals 1, and then we can sub 1 into our function and find that the maximum value is... Negative e seems low for a maximum value. Let's just check that that fits with the graph, that that's not actually a minimum. So I'm just going to have a look at sketching the graph of h of x, just so I can check. See, that's a minimum. So the maximum value is actually going to happen at one of those end points. And looking at, so 0 to 2, 0 is obviously not the maximum over that domain. 2 looks like it's that x-intercept. Sorry, should have had a look at it first before I did anything. So h of 0 obviously is negative 2, h of 2 is 0. Okay, so 0 in this instance is actually the maximum value of this function. And that's where sometimes function max is a safer algebraic option, because it's derivative equal to 0 is going to give you any stationary point, whereas function max, so if we go to menu for function maximum, option 8, and if we'd found the maximum of h of x, oops, sorry. Now, if we just typed this in, h of x comma x, it would have told us the maximum is when x is infinity, and that also makes sense given the graph because I haven't restricted it. So you would need to give it that restricted domain for it to tell you which endpoint the maximum's at. I apologise if you can hear some strange noises. I have a neighbour making some strange noises. Just a lot of banging. So sorry if you can hear that. Sometimes you can't predict these things. Okay, so that confirms that the maximum is at x equals 2, and then obviously to find the maximum, so function max doesn't give you the maximum value, it gives you the x value where the maximum occurs, and so then you'd need to substitute that in. And so this is where having defined the function's efficient. Even if I typed the function into the function max here, then I would have needed to sub 2 back into that function, so again, always helpful to have defined the function, even if just for a multiple choice question. Okay, so option B for question 4. Okay, so question 5, consider the following 4 functional relations. Okay, so f of x equals f of negative x, so that's an even function. It's even. Negative f of x equals f of negative x, that's an odd function. That's not any function. That f of x equals negative f of x, it just means that if you were to reflect the graph in the x-axis, it's still the same graph, so that means it's symmetric about the x-axis. And then f of x all squared equals f of x squared. Okay, so the number of these functional relations that are satisfied by the function f of x equals x is, okay, so it's a nice simple function, so definitely quick enough to do it by hand, although we could use a CAS here if we needed to or wanted to. So obviously thinking about this functional relationship, f of x is x, and that does not equal the same thing as f of negative x, so that one's not true. The next one, negative f of x, would be negative x, and that is going to be the same as f of negative x. Okay, so f of negative x means wherever there's an x in the function, you replace it with a negative x, and so that is the same as multiplying the whole function by negative 1. So that one is going to be true, the second one. It's an odd function. F of x equals negative f of x, well that's not going to be true because f of x would be x and negative f of x would be negative x. And f of x all squared obviously is going to be x squared, which would be the same as putting x squared into the function and getting x squared, so this one would be true. So it's 2 of those that are true, so option C. Okay, so question 6. The probability of winning a game is 0.25. The probability of winning a game is independent of winning any other game. Okay, so we have a binomial situation. We either win or we don't win. We know what P is, it's 0.25. The independence is telling us it is binomial. If Ben plays 10 games, the probability he will win exactly 4 times is closest to. Okay, so this is just a straightforward binomial question. So W is the number of wins. W is binomial, where N is he plays 10 games and the probability of winning is 0.25, and we want the probability of W equaling 4. Now we could use our binomial formula if we want, which would mean we get 10 choose 4, 0.25 to the power of 4, and therefore 0.75 to the power of 6, and type all that in, but we're going to have to put that in our CAS anyway, so I'm just going to use the binomial function. So menu 55. A for binomial PDF, so that is where we want a single value of W. So our number of trials is 10, probability of success is 0.25, and we want the probability that W equals 4. And so that is 0.145998. So it's going to round to 0.1460, so option A. Sometimes, if these options had been presented to us as fractions, menu 55A by non-PDF is never going to give us an exact answer. So in that case, we would use this, and we would use 1/4 and 3/4 and get it nice and exactly. But that's fine in this instance. Question 7. The tangent to the graph of this cubic at x equals 1 passes through the origin. The value of A is... Okay, so if we think about what we have here, we have some sort of cubic function. Doesn't matter what it is. I'm not too stressed about it. Y intercept at 1, so I'm just making it up. Okay, so what we know is, that's not going to be helpful. Alright, let me draw it. I'm just trying to illustrate to you what's going on here. Sorry. So what have we got? X cubed. So having sketched the graph now, I've defined the function as f1 of x, so I can use that over in the calculator screen if I want to do any algebra with it. No, I don't want a. Sorry, I'm not constrained all today. I'm going to hit cancel on that. And I'm going to just make a1, just so we get an idea of what the shape is. Okay, so let's say we have something like that. And we're saying that the tangent at x equals 1 passes through the origin. Okay, so that's what we've got going on. Sorry, it's at x equals 1, and it goes through the origin. So what that means is, if we can work out the coordinates of the point where the tangent, if we work out the coordinates of that point, okay, so if I substitute 1 into this function, so f1 of 1, it's 1, okay, so that's the point 1, 1. And we know the origin is the point 0, 0. So we know that the gradient of this tangent has to be 1, which means that, of course f1 was 1 because f1 has got a equals 1 in it. Sorry, okay, let's start again. So let's define the function with a in it. So it's not going to be 1, 1 either. So, I mean, we could do it pretty easily. It's going to be 2 minus a if we sub 1 into that. So that'll be 1, that'll be minus a, and that'll be 1. So we get 2 minus a. And so what we want to do here is use the fact that there's 2 different ways to calculate the gradient of this line. It's not 1, okay. So there's 2 different ways to calculate the gradient of this line. We could do the gradient using rise over run, okay. So the gradient is going to be rise over run, which in this instance would mean that it's 2 minus a over 1, so it's 2 minus a, so that's the gradient. But we also know the gradient is the derivative at this point, f dash at 1. And then we can equate those 2 expressions. So let me just finish defining the function here. So we're going to have x cubed minus a times x squared and plus 1. Okay, so if we do shift minus to differentiate, differentiating f of x at, so given that x is equal to 1, okay, so that is 3 minus 2a, and so therefore these 2 things must be the same. You can find the equation of the tangent in terms of a and sub in the point 0, 0 into that. That's another way to do it, but often there's just a bit less ugly algebraic expressions to write down when you just equate the gradients. So 2 minus a equals 3 minus 2a, adding 2a gives us a on this side, and subtracting 2 gives us 1 on this side, and so a must equal 1, which is option B. As I said, the other way you could do it is you could find the equation of the tangent at x equals 1, so get your CAS to do that, menu 49, tangent line to f of x when, sorry, my calibration seems to be a little bit out over here, when x is equal to 1. Okay, so there's my equation of the tangent, and then obviously I know that that tangent line goes through the point 0, 0, so you would say the tangent at x equals 1 is going to be y equals negative 2a minus 3 times x plus a minus 1, and then we know that that tangent has to go through the origin, so we'd sub the point 0, 0, and then we can solve that. So obviously this whole thing here becomes 0, and so 0 is going to equal a minus 1, and so a equals 1. So 2 different ways you can do it. Okay, question 8. The graph of the function f is shown below, graph corresponding to f dash. So the derivative, therefore, is which of the following? So we want to sketch the derivative function. So the derivative function has to have the same domain as the original function. You can't have the gradient of the function if you don't actually have the original function. So they have to have exactly the same domain. So it's definitely not going to be this one. It's definitely not going to be this one. It's definitely not going to be this one. So it has to be C or E. And the main two differences I'm looking at there is in this one, our derivative function is completely below the x-axis, and so therefore that's saying the gradient's always negative. In this one, the derivative function is completely above the x-axis, so that's saying the gradient's always positive. And we can see here that the gradient is indeed always positive. It starts off as a big positive value, and it gets to be a smaller and smaller positive value. So something of this kind of shape is going to be the gradient function, so option E. Okay, question, sorry, that'll rectify itself in a minute. There we go, question 9. Let g of x equal x plus 2 and f of x equal x squared minus 4. If h is the composite function given by that, then the range of h is. Okay, so f of g of x is substituting f of x into g of x. So that means wherever there's an x in g, we're going to replace it with that whole function g of x. So we're going to have, sorry, function f of x. So we're going to have x squared minus 4 and plus 2. And so therefore we have x squared minus 2. And so x squared minus 2 obviously is a parabola down by 2. But we only have it over this domain. And so, sorry. So this is the point 0, negative 2. So I'm just going to work out those two endpoints. So h at negative 5 is going to be negative 5 squared minus 2. So obviously 25 minus 2, so 23. And h at negative 1 won't be that high, I'm sure, but let's just confirm. And so 1 minus 2, so it's a negative 1. Okay, so we've essentially got, if we then restrict the domain, obviously I haven't got my scale right here, but it includes negative 5. It's going to come down here, and then it comes back up. Oh no, it doesn't, sorry, I'm only going to negative 1. A hollow circle at negative 1. So negative 1, negative 1, and 25, negative 5, 23. Okay, so we can see that the range is therefore going to go from negative 1, not including negative 1, up to 23, including 23. Have I done the composition round the wrong way? Yes. Let's try again. Sorry, I did the composition backwards, so I'm dealing with the wrong function. Let's delete all of that, and let's try again. So we're doing f of g of x, which means it is g that we are substituting into f. Okay, so wherever there's an x in here, we're going to replace it with g. So my apologies for that. Okay, so this is going to be x plus 2 all squared minus 4. So that's a parabola with its happy parabola with its turning point at 2, negative 4. So again, my scale's not going to be right here, but that doesn't matter. Just in my head, I'm working out where the y-intercept is. So when x equals 0, it's going to be at 0. Okay, so 2, negative 4. Y-intercept's at 0, 0. If I sub 0 into here, I'm going to get 2 squared minus 4, which is 0. And again, we've got that restricted domain though. So we're only going to be dealing with a bit of the graph over here from negative 5 to negative 1. Obviously I haven't got very good scale again. So let's try again. So this time when h is negative 5, when x is negative 5, so h of negative 5, we get negative 5 plus 2 all squared plus 4. So it's negative 3 squared, which is 9 plus 4. So it's going to be 13. And h of negative 1 is negative 1 plus 2 all squared, so it's 1 squared, which is 1, plus 4 is 5. Okay, so my graph goes from the point negative 1, 5, up to the point negative 5, 13. And we still haven't got an answer. F of g of x. Oh, turning point's at -2, -4, but that shouldn't change these numbers that I've worked out here. It's a very simple question. What have I done wrong? Oh. Clearly shouldn't be recording today. Okay, so this is a minus. So it's minus, minus, minus. And so 9 minus 4 is 5, and 1 minus 4 is -3. So let's try that again. That's -3. My graph's obviously not right because the turning point's at -2, 4. That's okay. The endpoints are all we need, and this is at -5, 5. Okay, so this is a not included point, and this is an included point, so my range goes from -3 not included up to +5, which is included. So it should be option A. Give my track record there. I'm just going to check that solution. Okay, and it's a really good thing I checked that solution. Boy, let's hope things improve, everybody. Let's try again, because the graph sketch being wrong does matter. Let me start again. Okay, so, as I said, we're substituting this function into this function. We get x plus 2 all squared take away 4, which means the parabola has its turning point at -2, -4. Let's try that again. Okay, so then the calculations I did previously in terms of h of -5 being -5 plus 2 squared minus 4, which is 9 minus 4, which is 5, is correct. H of -1, that calculation also ended up being correct. 1 minus 4 is -3. Okay, so what we have here though is that is the point. That there is the point -1, -3, and this up here is the point -5, 4. Obviously things aren't to scale. That is the graph, and so the turning point is within the domain, and so therefore the minimum point of the graph is at -4 at the turning point, and the maximum point is at sorry, I've drawn that wrong again, isn't it? That's 5, at +5. So we're going from -4, including -4, up to +5, including +5. So this open endpoint is not actually to do with the range. The range is from the turning point up to that maximum point at -5, 5. And so E is the correct answer here. Okay, let's hope things look up. Question 10. Consider the functions f of x equals square root of x plus 2 and g of x equals 1 minus 2x defined over their maximal domains. The maximal domain of the function h equals f plus g is. Okay, so the domain of f, square roots, obviously the thing under the square root has to be bigger than or equal to 0 for the square root to be defined. So that means x has to be bigger than or equal to -2. Okay, so this means that the domain of f is from -2 to infinity. Again, square root, so that thing under the square root has to be bigger than or equal to 0. So 1 has to be bigger than or equal to 2x. Half is bigger than or equal to x, so x is less than or equal to a half. And so that means that the domain of g is from -infinity to a half, inclusive. And then a composite function, sorry, not composite, a sum or product function is only going to be defined over the intersection of those two domains. So the domain of h is the intersection of the domain of f and the domain of g. So the intersection of these two sets here is just going to mean that we're going from -2 to +1/2, inclusive of both. So D. Okay, so question 11. If the integral of f of x from 0 to a is k, then this is Okay, so we just need to split this integral up using our properties of integrals. So this is the same as the integral from 0 to a of 3 times f of x plus the integral from 0 to a of 2. So I've just split up that addition. Then I can take this 3 outside of the integral. So that is 3 times the integral from 0 to a of f of x plus the integral from 0 to a of 2. And obviously this is what we've been told. We know that that is k. And so we're just going to have 3k plus, we're going to need to integrate 2. So we get 2x, we're doing that from 0 to a, so we have 3k plus 2a minus 2 times 0, and so we just have 3k plus 2a, so option A. Okay, so for a certain species of bird, the proportion of birds with a crest is known to be 3/5. Okay, so that's p, that's the population parameter. Let p hat be the random variable representing the proportion of birds with a crest in samples of size n for this specific bird. The smallest sample size for which the standard deviation of p hat is less than 0.08 is. Okay, so we're going to need standard deviation of p hat. We've got our formula sheet with us. Standard deviation of p hat is on the formula sheet. There it is there. So standard deviation of p hat, square root of p times 1 minus p on n. Okay, so we know standard deviation of p hat, square root of p times 1 minus p over n. Okay, so n is what we're trying to find. We know the standard deviation of p has to be less than 0.08, so this has to be less than 0.08. We know what p is, it's 3/5. So we have square root of 3/5, 1 minus 3/5 is 2/5, on n has to be less than 0.08. We'll get our case to solve that. Sorry, pressed the wrong button there. Oh dear. Okay, so I'm going to have 3. Get there in a minute. 3/5 times 2/5 over n, and that has to be less than 0.08, solving for n. Okay, so that means n has to be bigger than 37.5. N's obviously a sample size, number of birds, and so that means n is going to have to be at least 38. So the smallest sample size is 38, so D. Question 13. The value of an investment in dollars after n months can be modelled by this function, where n has to be a, I was going to say positive integer, but positive integer with 0. The average rate of change for the value of the investment over the first 12 months is closest to. Okay, so n is in months, good. So we just need to work out f at 12 minus f at 0 over 12 minus 0. So average rate of change, remember, is just the average gradient, so it's just the gradient of the straight line joining those 2 points. And so probably quickest for me to define the function, and then I can work that out. Sorry if you can hear some strange noises today. My headphones aren't staying on my head. So defining f of n is equal to 2,500 times 1.004 to the power of n. And then I just need to work out f at 12 minus f at 0 over 12 minus 0. And so that is 10.22. Try that again. 10.22. So $10.22 per month. Closest to, so closest to $10.20. It's a bit strange that they've rounded it to the nearest 10 cents, but okay. Sort of more of a further maths thing to do. But anyway, even then, generally speaking, monetary things round to the nearest cent. So question 14, a value of k for which the average value over the interval from 0 to pi is equal to the average value of y equals sine x over the same interval is. Now I'm sure there's a fancy way we could think about this graphically, but with our CAS in hand it's just going to be quicker to work these things out. So the average value of y equals sine x over that same interval is going to be 1 on pi minus 0, integral from 0 to pi of sine of x. Sorry, I keep pressing shift when I mean to press control. So that's going to be 1 on pi, shift plus, from 0 to pi of sine of x. I just realised I'm in degrees from a question I did in a previous exam. Just change that to radians. Okay, so that is 2 on pi. And then we want the value of k, for which the average value of this function is going to be the same as this. Okay, so now we know over that same domain, so 1 on pi minus 0, so 1 on pi, integral from 0 to pi, cos of kx minus pi on 2 has to be equal to 2 on pi. We'll solve that for k. So we're going to solve 1 on pi, integral from 0 to pi of cos. Now be careful when you type kx, you're going to need that implied multiplication. It won't be implied, so you need to be explicit about it. If you just type k and x next to each other without anything in between them, it'll just assume that is the name of the variable, kx, and it won't distinguish, there won't be any k's in here to solve. And I would hazard that that was probably a reasonably common error in this question, where people just couldn't get it to actually solve anything. Equals 2 on pi, and we're solving for k. Okay, so we're over the interval from 0 to pi, so obviously the negative solution's not in that interval. 0.5 and 1 are both going to be in that interval, but 1's not an option, and so it has to be 0.5, so option E for us here. As I said, the error that would have been, I think, reasonably common would have been to have left the multiplication out of that cos and then have got a sort of ugly general solution because it actually can't solve for k. You see here it's actually solving for kx. It's actually solved for kx because it can't see k, it's just rearranged the formula. So do be careful about that importance of putting the multiplications between two variables. Okay, question 15. 4 fair coins are tossed at the same time. The outcome for each coin is independent of the outcome for any other coin. The probability that there is an equal number of heads and tails, given that there is at least one head, is... Okay, even though there's 4 coins, we could still essentially treat this as being the same coin being tossed 4 times. It's not going to make it any different. So we're interested in heads. So if h is going to be the number of heads, h is binomial. We're tossing the coin 4 times, or we're tossing 4 coins. There's a 50-50 chance of being a head. Independence means we can use binomial. The probability that there is an equal number of heads and tails, so equal number of heads and tails would mean 2 heads and 2 tails, so that's going to be probability that the number of heads is 2, given that the number of heads is at least 1. So conditional probability, we need the intersection of these two things. If we need both 2 heads and at least 1 head, that's just 2 heads over the second thing. I'm going to need fractions here. Let's see how ACAS does, just using binom CDF rather than doing it exactly. Hopefully we'll be able to get close enough. So menu 55A for the numerator. So n is 4, p is half. C, p is half, and h is equal to 2. Okay, so that is 0.375, so it's not a rounded decimal, so that's fine. And then menu 55B. So number of trials is 4, probability of success is half. Sorry. Need to recalibrate over at the side here where the CAS is. And the lower bound we want greater than or equal to 1, so lower bound is 1 and upper bound therefore is 4. And so that is 0.9375, which I also don't think is rounded, so I think we'll be fine to get a fraction when we do this division, or get a nice exact answer anyway. Okay, and that's not even approximately equal to, it's actually equal to 0.4, which is 2/5, so D. Okay, question 16. Let cos of x equal 3/5, sine squared of y equal 25 on 169, where x is between 3 pi on 2 and 2 pi, so that's the 4th quadrant, and this is also the 4th quadrant. So x and y are in the 4th quadrant. The value of sine of x plus cos of y is, okay, So the first thing to realise is this one here. This means that sine y all squared is 25 on 169. So sine of y is plus or minus 5 on 13, which is a square root of 25 on 169. But because we're in the fourth quadrant, and we know that sine, which is the y coordinates in the unit circle, is negative down here in the fourth quadrant. So that means that sine of y is going to be negative 5 on 13. Okay, so now let's think about what we want here, because we actually need to reverse. So cos of x is 3/5, but we need to know what sine of x is. Okay, so we can use the Pythagorean identity here. So Pythagorean identity says that sine of x squared plus cos of x squared is equal to 1. And that simply comes from the unit circle definitions of sine and cos. Okay, so sine is the y coordinate, which means if I draw a right angled triangle in the unit circle, its hypotenuse is 1. Its height is sine of x, if that angle is x. And its base length is cos of x, because the x coordinate in the unit circle is cos. And so therefore you're just using Pythagoras' theorem in that triangle, sine of x all squared plus cos of x all squared equals 1 squared. Okay, so in this case, we know that cos x is 3/5. Okay, so sine of x squared, I have to do that. It's 1 minus 3/5 squared. 3/5 squared is obviously 9 on 25. And so 1 minus it's 16 on 25. And so therefore sine x is going to be the square root of that, so plus or minus 4 on 5. But again, we know x is in the fourth quadrant. And so that's going to mean that sine of x is negative, so negative 4/5. And then I need cos of y. It's the same thing, Pythagorean identity with the sine value here to get cos. So I'm going to run out of space here. So let me just make things small. You might not be able to read them anymore, but let's just make them tiny so we can move that out of the way so I've got room to write the other one. So then we also know that sine of y squared plus cos of y squared is 1. And so that is, well, we already know what sine of y squared actually is. We know that's sine of y squared. So 25 on 169, so actually we didn't even need to do this bit. Plus cos of y all squared is 1. So cos of y squared is 1 minus 25 on 169. That's going to give me 144 on 169. And so cos of y is going to be the square root of that. So it's going to be plus minus 12 on 13. But y is in the fourth quadrant and cos is positive in the fourth quadrant. So y is in the fourth quadrant, cos is positive, and so cos of y is going to be positive 12 on 13. Okay, so now, as I said, we didn't actually need this bit, so let's get rid of it and clear ourselves some space. Now. Okay, so we want to find the value of sine x plus cos y. So sine of x plus cos of y. Sine of x we worked out up here is negative 4/5. Plus cos of y we've worked out is positive 12 on 13. So let's get our CAS to do that for us. Negative 4/5 plus 12 on 13. Is going to be 8 on 65. So option A. Okay, question 17. A discrete random variable x has binomial distribution with a probability of success of 0.1 for n trials where n is greater than 2. If the probability of obtaining at least 2 successes after n trials is at least 0.5, then the smallest possible value of n is. Okay, so x binomial, we don't know what n is, we do know what p is. We know the probability of obtaining at least 2 successes has to be at least 0.5. Okay, so I'm going to use inverse binomial n here, and that requires me to reframe this statement. So this is the same as the probability of x being less than or equal to 1 has to be less than 0.5. Okay, that lets me use inverse binomial n. This 1 and this 0.5 are what I'll use. Obviously, if this number had been something other than 0.5, this number would be 1 minus that. So it's hard to see that when they're both 0.5. So menu 5D for inverse binomial n. Cumulative probability. So because cumulative probability is why we have to reframe this to be a less than or equal to, because it needs to be cumulative from the smallest values of x up to what is that probability. And so that's why we have to flip the statement around to use inverse binomial n. So the cumulative probability is 0.5. The probability of success is my p-value from my binomial distribution, that's 0.1. The number of successes is going to be this number here when I've reframed the inequality to be the right way around, and it must be a less than or equal to inequality, so it needs to be 1. And that tells me that n is going to have to be at least 17 for that to be true. You can also do these questions just as a trial and error. So we could have just done, rather than flip it around, we could have just stayed back here. We could have done menu 55B. Number of trials is unknown. Let's just have a guess. Let's guess if we do 10 trials. Probability of success is 0.1. We want to go from 2 to 10. And we want that probability to be at least 0.5, so that's quite a long way off. So maybe I jump up to 15. And you just edit it until you, edit it until you get the probability you want. Okay, we're getting close. Then we try 16, we try 17, we would find that it would be 17. So before, inverse binomial n is a relatively new addition to the TI Nspire CAS. And before that, the only way to do this was via trial and error, and actually it's still reasonably efficient because you don't have to worry about that reframing and getting the information all in the right order to be able to use inverse binomial n. So you can see here that when n equals 17, that's the first time that that probability is over 0.5. Obviously 18 and 19 would also give you a probability greater than 0.5, but it asks you for the smallest possible value of n. Okay, let f be this cubic function with domain R, let g be this product of a linear and a log function with domain from -infinity to 0. That's not a restricted domain though, that's just the domain that's the implied domain that's necessary for this log function to be defined. The maximum number of solutions for the equation f of x minus k equals g of x. Okay. Let's just think a little bit graphically about what's happening here. I wonder if we could just sort of solve it and draw some sort of conclusion, but I actually think this is probably going to have a reasonable graphical application. Let's draw them both over here so we can see them on the same axes. So I'm going to draw 2x minus 1 times 2x plus 1 times 3x minus 1. So we're going to be quite close together there because those intercepts are at plus or minus a half and at a third. So I'm just going to bring these axes right in so we can see what's going on. Even we probably don't need this to be so low. Okay, you could play around with it a bit more if you want, but let's just go with that. Let's put the other function in as well. So let's put in x times log e of negative x. Okay, so there's that function there. So we can see without, so what we're saying here is we're going to do a horizontal translation to f of x, and we want to think about the maximum number of solutions we could get. So let's maybe actually edit this so we can play with it. Actually, let's do another one. So I'm going to do this time sketch, sorry, f2, which was the log function of x minus k. It's going to ask me if I want a slider, and I'm going to say yes, because I'm going to have a play around with it. Okay, so things are going to get pretty crowded on the handheld. I'm actually going to move to using a mouse just to help me control it a bit better. I'm going to get rid of that red graph so it's not in our way. Just going to turn that one off. And I actually might just make that one's colour something a bit brighter so we can see it. Okay, so at the moment k is, the other thing I'm going to do is edit, sorry I hate working with the sliders. Ooh. I'm going to minimise that, it just makes it easier for you to control the controls. Okay, so, and we might need to adjust its settings as well. Okay, so if k equals 1, we might actually, given we're dealing with quite a small scale, I think we're going to need to change the settings here. I really don't recommend, let's make that like 0.1. I really don't recommend having to do a slider in an exam, although I am noticing, and I am recording this in 2024, and I have noticed in the last couple of years that there have been multiple occasions, sorry, I'm trying to move that out of the way. I'm having zero luck. Okay, I'm going to give up. There have been multiple examples. It's really in the way though, we can't see the intercepts very well. Let's make things smaller here. See if that'll let me grab it now that I've done some adjusting. Nope. Ah, there we go, okay. Just going to get that out of the way. There have been multiple examples in recent years where actually using a slider has been a useful thing to do, and to that end, you know, I think it's worth having a little play around with them, but they are a real pain. They're not very user-friendly. They're hard to move around once you get them. They're really hard to get rid of once you get them. So I would tend to, I think you're probably better to do it in a document where you could just start a new document so that you haven't got the K. Because what's happening now is this letter K is now defined as a number, and that can cause problems later on if you don't properly get rid of that slider. Okay, so let's have a look. So we can see here, as I'm making K bigger out here, it's intersecting once down over here, okay, and it's always going to intersect once. Even though we could move it as far as we want over here, those are still going to intersect down there off the screen, okay. So it's definitely going to intersect once if we go out in this direction. We can move in, and we see there's going to be a point, there's going to be a point somewhere here where it'll just be tangent at that point and intersect once over here, so we'll get 2 points of intersection. We're then going to be able to move in this way and get 3 points of intersection. So we can definitely get 3. Let's see if we can get 4. I don't think there's going to be a way for us to get 4. I'm just thinking about the shape of it. I don't think there's going to be possibly a way for 4. We've got going to have 2 there. We're still going to sort of have 2 there. You'll have a kind of tangent one and one over there. And then, you know, you can get none over here. So it'd be possible to get none. It's possible to get just 1. It is possible to get just 2, and it's possible to get 3. But I can't see any way that we would get 4 solutions. So option 18 is going to be 3. Okay, so now let's just quickly talk about getting rid of a slider. So as I said, if you're in a document, Control-N, create a new document, start again. I'm in the scratch pad, so I'm going to want to keep using it. I'm going to do delete, delete, delete 3 times. Oh, that was much easier than it should have been. Sorry, I'm going to undo that. Because it's not usually that easy. So it was because I was clicked on it, then when I hit delete, it just deleted that. So delete, delete, delete 3 times always gets rid of everything. That's the easiest way, but it doesn't get rid of sliders. And so then if I'm going to need to go up here and click on it and a right click, so right click on your handheld is to do control menu, and then you can go delete. But you need to be careful over here, because if I type the letter K, it's bold and it's still defined as that value that was in the slider. So I'm also going to need to do a clear A to Z, a new one for. Now let's check. If we do k, it's not. It's just k again now. So it's one of the things I hate about sliders. I think they're really fiddly on your handheld to have to do in an exam. But as I said, in recent years, I'm seeing that there's sort of at least 1 or 2 questions on each exam where it is a useful thing to be able to think about and use a slider. Okay, question 19. Which of the following functions is differentiable for all real values of x? So we need to make sure that they're continuous and smooth to be differentiable. And so a definitely isn't. So if we have a think about a, that is y equals x when x is bigger than 0 and y equals negative x when x is less than 0. And so whilst it is continuous because the graphs join here, it's not smooth here, so not differentiable. B, I'm going to draw on the same axes. It's y equals x when x is less than 0, so it's going to be that bit down there, and negative x when x is bigger than 0, so that bit there. Again, they join here, so it's continuous everywhere, but not differentiable here because not smooth. So definitely not this one. Alright, so we're going to want to think about these different functions here. So we might actually, graphing them is going to be time consuming, isn't it? We really just want to be able to think, first of all, do they actually join? So when x equals 0, this part of the function is going to be 4, this part of the function is going to be 1 squared, it's going to be 1. So they don't even join at 0, so it's not a continuous function. So that's definitely not going to be differentiable at 0. This one here, x equals 0, is going to be 1. When x equals 0 here, it's also going to be 1, so these ones join. Just checking this one, these ones join as well. Okay, so now what we need to decide here, so again, multiple choice is process of elimination, first of all, should be what we're thinking. Okay, so both of these join at 0, 1. So now we need to work out which one joins smoothly at 0, 1. Okay, so if we think about this one, the derivative of 2x plus 1 is just 2, so the gradient of this branch at 0 is going to be 2. The derivative of the other part of the function, 2x plus 1 all squared, is going to be a chain rule, so 2 times 2x plus 1 to the power of 1 multiplied by derivative of the inside, which is 2, so it's going to be 4 lots of 2x plus 1, and at x equals 0, derivative is going to be, it's not good notation, that can't equal anything, but go with it, it's just multiple choice. Derivative is going to be 4. Okay, so they don't have the same gradient where they join, so it's not going to be this one. By process of elimination, it's going to have to be this one. And actually, we can use what we found up here. Derivative of that will clearly be 4, so the gradient at 0 is going to be 4, and this is the same one as this. We know the gradient here is 4. So option E is going to be correct. So for functions to be differentiable, they have to be continuous. So that was the first thing I checked. They have to be continuous and smooth. So C wasn't continuous. All of the others were continuous. They joined, but these two didn't join smoothly. We could see that graphically without having to do any calculation. These two didn't join smoothly. We had to do a bit of calculation to confirm that. And so option E is our only other option. You could obviously have graphed them all, which would have shown you whether they joined, and you would have been able to get some idea from looking at them whether or not they joined smoothly. But graphing those 5 piecewise functions was going to be pretty time consuming as well, so either way it's not the most efficient one, but not a particularly difficult question for question 19. In fact, I must say my impression of this set of multiple choice questions compared to other exams is that this is a relatively straightforward exam. There's been nothing particularly curly here at all. Okay, question 20, the last of the multiple choice. Let A and B be 2 independent events. Okay, so independence, we need to know what that means. If events are independent, probability of A given B is just the probability of A. The fact that B happened doesn't matter at all. We also know we can manipulate that to find the probability of A intersection B is the same as the probability of A times the probability of B. Okay, so we need to know that those are properties of independent events. They're going to be required. Okay, probability of A is P, probability of B is P squared, probability of A plus B is 1, probability of not A union B is equal to. Okay, let's have a think about things here. Could probably set ourselves up some kind of diagram just to help us. So let's maybe do a Carnot map just to help us organise things. Everything should add up to 1 down here. Probability of A is P. probability of B is p squared. Probability of A plus the probability of B is 1. Okay, that would allow us to work out P, but we don't need to work out P. We want probability of A plus B is 1. Okay, so these two things are added together are 1. I don't think that's overly useful just yet. Let's see where that comes in later on. These obviously 1 minus p squared, 1 minus p, but to use a Carnot we need to know at least one thing in here. But actually if we go back to our independence, we know that A intersection B, which is this cell up here, is probability of A times the probability of B. So it's going to be p squared times p, so it's going to be p cubed. Okay, so that's using our property of independence. And from there then we can fill in what we don't want. So we want probability of not A union B. Okay, so probability of not A union B is everything in, oh sorry, no, not that. It's going to be everything in, yeah, not A, which is those things, and everything in B. So it's going to be those three areas for this union, which means it's always quicker for a union to do 1 minus something. So it's actually going to be 1 minus this thing here. So let's do it that way. So this thing here is going to be p minus p cubed, just using the Carnot map. So the total probability here is p minus this probability is p cubed. And so then we're going to have probability of not A union B is the same as 1 minus the probability of A and not B, which means it's 1 minus p cubed. So it's going to be 1 minus p plus p cubed. Let's hope that's an option. Option D. Okay, that brings us to the end of the multiple choice. So let's move into the extended answer questions. Alright, so question 1. Rectangular sheet of cardboard has a width of h centimetres. Its length is twice its width. Squares of side length x centimetres where x is bigger than 0 are cut from each of the corners as shown in the diagram. The sides of the sheet of the cardboard are then folded up to make a rectangular box with an open top as shown in the diagram below. Assume that the thickness of the cardboard is negligible and that the volume of the box has to be greater than 0. Okay, this is a really, really routine Year 11 polynomial cubic application question. You should, in your lifetime, have done 20 of these at least. When I saw this in the exam in 2021, I remember almost laughing and thinking, gosh, this is very routine. And as I said to you before, I think the multiple choice were quite routine in this year. I think this extended response was quite routine. I can't remember what comes after this, but from memory, I think this was a reasonably routine paper. And I suspect that was a little bit out of kindness. 2021, obviously, we spent a lot of 2020 and 2021 in lockdown. There was no study design adjustment in 2021, whereas there was in 2020. We taught less content. So we still had to cover all of the same content throughout a lot of lockdown in Victoria in 2020 and 2021. So I think this exam is possibly a reflection of that, and I do think this was a relatively straightforward exam in the scheme of things. Okay, so we've got this very standard problem where we make a box by cutting the corners out of the cardboard and folding it up. Show that the volume of the box is given by this. Again, very routine. So obviously thinking about the dimensions of this box, so this base length along here is going to correspond to this length here in my diagram. Sorry, I should have changed colour there so you could see where I was drawing. So these are going to be the same. Okay, and so therefore that length is going to be 2h, which is this total length, minus 2 lots of x. Okay, so we're going to have 2h minus 2 lots of x, and then this length here is going to be, sorry, this length here is going to correspond to this length here in the net, and so that is going to be h minus 2 lots of x. And then when you fold up the sides, that is going to come from this. Okay, so if we fold up the side length, that's going to give us, fold up those sides of the box, that's going to give us that. And so x is the height of the box. And so therefore the volume of the box, use the same notation as the question, is going to be equal to 2h minus 2x times h minus 2x times x. and then we obviously just need to manipulate it to get it in the right form. Oh, we want h to be 25. Okay, so let me just tidy this up first. So I'm going to take out the common factor of 2. I'm going to write that x at the end, at the beginning. I should have done that to start with. So we have 2x. I've taken the 2 out of that first bracket, so it's h minus x and h minus 2x. And obviously I missed the fact that h is 25. So when h equals 25, the volume of the box is going to be 2x times 25 minus x times, sorry, I wrote 25 up there. Can't talk and write something else at the same time. And this will be 25 minus 2x, which obviously is in a slightly different order than that one, but the same thing. Okay, so we've shown the volume of the box. State the domain of v box. Okay, so I might actually define my volume function. Obviously I'm not going to define it with the box bit, so it's going to be v of x. Volume in terms of x is 2x times 25 minus x times 25 minus 2x. Okay, so these are always fairly routine. So if we think about this as a cubic function, it is a negative cubic. We take negatives out of both of those. Obviously that's not what we need to show, but it's going to be the same as if we take negatives out of both of them. Actually, it's still going to be positive cubic, my apologies. It'll be 2x times x minus 25 times 2x minus 25. So it's positive cubic, intercepts at 0, 25 and 25 on 2. So therefore we're going to have this 25 and 25 on 2. That's essentially the function. So in part B, where it says state the domain of v box, given that v box has to be bigger than 0, we're only interested in this part of the function, and so therefore we're only interested in, and it has to be greater than 0, so can't include that. We're only interested in that bit there. Now, we don't include this bit here because whilst we're theoretically getting positive volume over here, the only way we're getting positive volume is because both of these numbers here would be negative. For example, if you put h equals, let's go back to this other function. If you put x equals 30 into this function, for example, if you put 30 in here, and I need to put it in the actual, if you put 30 in here and 30 in here, you're going to get two negative side lengths, okay? You would get, you know, negative side lengths of -5 and -35. And so when they multiply together, you're overall getting a positive volume, but it's impractical. It doesn't make any sense, okay? So we're not looking at this bit over here at all. So the domain is just, oh, I knew that would happen. Just trying to get rid of that little red circle. Okay, not possible. Oh, give up. Okay, so we're just looking at our domain will be from 0 to 25 on 2. So the domain of VBox is going to be not including 0 and not including 25 on 2 or 12.5. Find the derivative of VBox with respect to x. Okay, I've defined my function, so I'm just going to differentiate it. Get my CAS to do that for me. Oops, sorry. Okay, so VBox dash is going to be 12x squared minus 300x plus 1250. I'm just wondering if we factorise that, so it doesn't factorise, so that's why it's given it to us in the expanded form. Calculate the maximum possible volume of the box and for which value of x this occurs. Okay, so I'm going to solve my derivative of my box equal to 0, so I'm solving 12x squared minus 300x plus 1250 equals 0. Solving that equal to 0 for x. Okay, and we're not given any rounding instructions, so we're going to give exact values. So we're going to have, I'm just going to get them as a decimal so I can see how big they are. So obviously my domain is 0 to 12.5, so the 19.7 solution is out of the domain, so I'm just going to give the first one. I hate the way the CAS factors out these negatives and creates these extra negatives. I'm going to expand that back out, so negative 25 times negative 3 is positive 75, negative 25, so it's 75 minus 25 root 3, which is what the answer would look like if we'd completed the square and got it ourselves. It always does this unnecessary factorisation. And so we've just got that one, since we know that x has to be between 0 and 12.5. Alright, so we want to calculate the maximum volume of the box and for which value of x this occurs. So we've calculated that bit, which value of x this occurs, and now we want to know the maximum volume. Maximum V box is going to be V of that ugly thing up there again. Alright, so I'm just going to write it this way, 75 minus 25 root 3 over 6. Okay, and so that is going to be 15625 root 3 over 9. And so that's our maximum possible volume. So we've got the maximum volume, the value of x for which this occurs, and some method for our third mark, which is solving our derivative equal to 0. Again, this is a very, very routine max-min application. Waste minimisation is a goal when making cardboard boxes. Percentage wasted is based on the area of the sheet of cardboard that is cut out before the box is made. Find the percentage of the sheet of cardboard that is wasted when x equals 5. Okay, so if x equals 5, let's go back here. We're now cutting out squares that are 5 by 5. So we're cutting out squares that are 25 square centimetres. We know that we still got h is 25, so this information, h equals 25, is in the stem of the question outside of any of the parts, so therefore it applies to every single part that comes after it. So we know that's 25, we know that's 50, so we've got a 50 by 50 sheet of cardboard, 50 by 25 sheet of cardboard, and we've cut out 4 squares of side length 5. Okay, so total area is going to be, so actually let's do total cardboard. Is 50 times 25. So 1250, was everything in centimetres? Yep, centimetres. So we can do some units on here. So this is centimetres squared and this is in centimetres. This is therefore centimetres squared. So the wasted cardboard is 4 lots of 5 squared, so 4 lots of 25, so 100 centimetres squared, and therefore the percentage wasted is going to be the amount that we wasted over the total amount of cardboard, and that'll give us a decimal, and then to change a decimal to a fraction we're multiplying by 100%, which is still just 1, so it's actually not changing the value, you're just changing what you write. So 100 divided by 1250 is 0.08, and so as a percentage that is going to be 8% of the cardboard was wasted. So yeah, question 1, very much early days, late year 10, early year 11, whenever you first do polynomial functions and their applications, you would 100% have done examples like this repeatedly. So a nice gift up until that point. Oh, sorry, we've got a little bit more, let's see. Now consider the box made from a rectangular sheet of cardboard where h is bigger than 0 and the box's length is still twice its width. Okay, so now we're going back to h is not 25. Let VBox be the function that gives the volume of the box. State the domain of VBox in terms of h. Okay, so we're generalising our function now. So now instead of h being 25, h is now h. Okay, so my function will have x-intercepts at h and h on 2, and so therefore the domain of VBox is going to be from 0 to h on 2. Find the maximum volume in terms of h. Okay, so I'm going to be solving the derivative of v box equal to 0. So let me take my CAS and redefine some things here and do all the same calculations again. So I'm going to define v of x, instead of there being 25 here, I'm going to make it h. 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 Okay, so then we're going to solve the derivative equal to 0, and that gives us h equals, now we want the first of those, so that's going to be, I'm just thinking about expanding that out, so it's going to be 3h plus h root 3 or 3h minus h root 3. So the minus one is actually the first of the two of them, so we definitely want that one. So we want 3h minus h root 3 over 6, because we know we have to be in this domain. Sorry, it's not h equals that, it's x equals that. So that's the value of x that gives us maximum volume. It didn't actually ask us for that in this question. And so then we want maximum volume of the box. We're going to substitute that back into our volume function. Volume of 3h minus h times root 3 over 6. And we get h cubed times the cube root of 3 on 9. Let's see if that works for 25. So let's do that. Given that h equals 25, and just check that matched the answer we got up here, which it did. 15625 root 3 on 9. So yeah. Okay, I think we've done what we need to do there. 3 marks, so it's quite generous. I think you'd still get the mark for the x value and the maximum and derivative equal to 0 being the method. Now consider making a box from a square sheet of cardboard with side lengths of h centimetres. Show that the maximum volume of this box occurs when x equals h on 6. Okay, so now this time we've got, this time we've got a square. Cutting out squares of side length x. The side length of the sheet of cardboard is h. Okay, so the volume, when we fold this up into its sort of tray-like box, these lengths are going to be h minus 2x, and this height is going to be x. So the volume is going to be x times h minus 2x squared. Okay, so thinking about that as a function, this x-intercept will be h on 2, so we're going to have, again, still positive cubic intercept at 0 and at h on 2, but it'll bounce there now. So the domain is still going to be from 0 to h on 2. To find the maximum, we need this turning point here, so we're going to solve derivative. So again, let me redefine my volume function now. We're going to have x times h minus 2x squared. And we're going to solve derivative equal to 0. And that's going to give us x equals h on 2 or h on 6. And we knew about h on 2, that's that x-intercept, there's a turning point there. Okay, and so our max volume is v at h on 6. That's all we need. Given that it's a show that, I think we possibly need a little more than that. I'm going to refer to my graph. Sorry, I'm just going to try and... In fact, given that it's a show that, I'm wondering whether we should possibly have shown a bit more algebra in this process. So generally speaking, I would write a bit more down. So let's actually work out what the derivative is and write it down. So derivative of, v of x. Sorry, I just launched into the same process we'd done before. Okay, so I would get my derivative is 2x minus h and 6x minus h, and that's going to have to equal 0. And so that means 2x minus h equals 0. And so x equals h on 2. And 6x minus h equals 0. So x equals h on 6. So it can be seen from the graph. So let's sort of formalize our graph a little bit more. This is x, this is v from the graph. That max v occurs when x equals h on 6. Okay. Question 2. 4 rectangles of equal width are drawn and used to approximate the area under the parabola y equals x squared from x equals 0 to x equals 1. The heights of the rectangles are the values of the graph of y equals x squared at the right endpoint of each rectangle as shown in the graph below. Okay, it's very explicit. We should have known all of that information. State the width of each of the rectangles shown above. Okay, so if there's 4 rectangles of equal width and they're spanning from 0 to 1, then each rectangle is going to have a width of 1/4 or 0.25. Find the total area of the 4 rectangles shown above. Okay, so the total area is going to be 1/4 times the height of this first. So this will be 1/4, this will be 1/2, this will be 3/4. Okay, so the height of that first rectangle is going to be the y value when x equals 1/4, so it's going to be 1/4 squared, plus the next rectangle has a width of 1/4, and its height is going to be the y value when x equals 1/2, so it's going to be 1/2 squared. And then 1/4 times the y value when x equals 3/4, so that's going to be 3/4 squared, plus its width is 1/4 and its height is 1. Okay, so we just need to work that out. A lot of fractions. 1/4 times 1/4 squared plus 1/4 times, forgot the bracket, sorry, 1/2 squared plus 1/4 times 3/4 squared plus 1/4 times 1 squared, so just 1. Okay, so that is 15 on 32. Find the area between the graph of y equals x squared, the x-axis, and the line x equals 1. Okay, so this is asking us to find the actual area. So we're going to need an integral to find this area here, bounded by those pink lines. And so that area is going to be the integral from 0 to 1 of x squared with respect to x. That is a pretty straightforward integral to do by hand. We've got our CAS sitting here. And so we're going to get 1/3. So these two should be relatively similar. Quite different actually. Well, actually if we look at it, the rectangles are quite a big overestimation. They're about 0.47, whereas the actual area is only about 0.33. Okay, the graph of f is shown below. Okay, have we met f before now, or is f an unknown thing? No, we've not met f. This is our first introduction. We don't know its equation, that's what its graph looks like. Approximate the integral from -2 to 2 of f of x using 4 rectangles of equal width and the right endpoint of each rectangle. Okay, so we need to be a little bit careful here because our graph is going under the x-axis, but this is not asking us to approximate an area. It's asking us to approximate a definite integral, and those aren't always the same thing. Okay, so we do need to be clear about that. So first of all, let's just set up the rectangles we're going to need. So we're going to approximate this using 4 rectangles of equal width and the right endpoint of each rectangle. Okay, so right endpoint of each rectangle is going to define the height. I'll use a different colour so we can see it on the axes better. So that's my first rectangle between -2 and -1. My next rectangle is going to be defined by the right endpoint, so it's going to be there. Again, right endpoint and right endpoint. Okay, so those are the rectangles. Now, if we're integrating from -2 to 2, part of that area is under the x-axis, part of it is above the x-axis. Now, if we were actually trying to find an area, we would need to do the integral from -2 to 0 of f of x plus the negative integral from 0 to 2 of f of x, but it's not asking us for an area, it just wants us to do this integral. So when we calculate these rectangles, they're going to have negative areas. So we're going to actually use the y values here. So we're going to use -6 as the height of that rectangle and -4 as the height of that rectangle. And I know the height can't be negative. I'm using that word height very loosely. Okay. So to approximate this integral, is going to be approximately equal to each rectangle has a width of 1, so the first rectangle has a width of 1 and a height of 6, plus a width of 1 and a height of 2, the next rectangle, plus the next rectangle width of 1 and a height of -4, because we're just finding a definite integral, it's not about area, plus a width of 1 times a height of -6. So we're going to have 6 plus 2 minus 4 minus 6, so they cancel each other out. 2 minus 4 is -2. And we should be able to confirm, oh, we don't know what this function is, I was going to say. And so that's the approximation using the right endpoint estimate. Okay. Parts of the graph of y equals x squared and y equals the square root of x are shown below. Find the area of the shaded region. Okay, so that area is going to be the integral from 0 to, we should probably confirm that they meet at 1, but I think they probably do. Let's solve x squared equals root x for x. Yep, 0 and 1. X squared equals root x gives x equals 0 and 1. So we're integrating from 0 to 1. Top function, which is root x, minus bottom function, which is x squared. Obviously, x squared and root x are inverse functions, so we could also use the line y equals x and double it, but we've got our cas, so there's no reason to do that. So integrating from 0 to 1, the square root of x minus x squared with respect to x. Okay, and that's going to be a third. Okay, the graph of y equals x squared is transformed to the graph of of ax squared, where a is somewhere between 0 and 2. Okay, so this is a dilation by a factor of a from the x-axis. Find the values of a such that the area defined by the regions bounded by the graphs is equal to a third. Okay, so we need to actually consider a couple of different things here. We've actually already looked at the example where a equals 1, and we found that that area was a third. Okay, so that's one of them. Okay, so but we also need to think about the two different things that can happen. So we know when a equals 1, the shaded area is a third. Well, that's because, yeah, the area from x equals 0 to x equals a, where a is 1, would be to x equals 1, and that's literally the example we've just looked at up there. Okay, So then we also need to think about these dilation factors in two different ways. Okay, obviously if we make a bigger than 1, we dilate away from the x-axis. And so what will happen is this graph, if we make a bigger than 1, will do this. Sorry, let me change the colour. The x squared graph will do this, and the square root x graph will therefore do this, because they're going to be what should I say? They're symmetric about y equals x still. Okay, and so this would be y equals ax squared, and this would be y equals, now if the inverse of that is going to be sorry, so we don't change the other one, it's still root x. Okay, so my apologies. So root x doesn't change. Okay, so this one is ax squared where a is bigger than 1. Okay, and so what we're going to have happen here then is that they're now going to intersect at, let's solve ax squared equals root x. Ax squared, a times x squared, sorry, equals square root of x for 4x. Okay, so they intersect at x equals 0, which we already know, and at x equals 1 on a to the 2/3. So I'm going to write that as a to the negative 2/3. Okay, so that point there is a to the negative 2/3. So that's smaller than a, right? If it's 1 on a to the power of 2/3, that is a number that is smaller than a, okay? Because a to the power of 2/3 is going to make, you're going to cube root it and then square it. So it's going to make a smaller, and then dividing that into 1 is also going to be smaller. Okay, so we've got, so therefore, when we're still talking about, it's the area from x equals 0 to x equals a. So if we assume x equals a is somewhere past here, then we're now talking about two different areas, okay? So we've got this area here, sorry, I've used the wrong, sorry. Okay, so what we've found is this point here. Okay, so we're going to need an integral to find that bit of area there, but there's also going to be some other area past here. Okay, so up there that we need to think about. So essentially what's going to happen is we're going to have, when a is bigger than 1 but less than or equal to 2, we're going to have this situation. And so the area is going to be the integral from 0 to a to the negative 2/3 of, this was the square root of x, minus ax squared. And we want to work out what a is when that equals a third. Okay, so that area has to be a third, so let's solve that for a. So we're going to solve, shift plus, we're going to integrate from 0 to a to the power of negative 2/3, and we're going to integrate square root of x, oops, not times, minus a times x squared with respect to x, and then plus, shift plus, the integral from a to the power of negative 2/3 up to a of, in that case, the parabola is the top function, a times x squared minus the square root of x dx, and we want that whole thing to be equal to a third, and we want to solve that for a. And we want 2 decimal places, good. So when we do this, a could be 1, which we already know about. When a equals 1, the area is a third. So where this is when a is bigger than 1. So we're looking at only over this domain. So that is 1.13. And then obviously we also have the situation when a is between 0 and 1. Okay, and if a is between 0 and 1, the a is going to squash the graph down. And so what we're instead going to have is, so if we go back up to here, instead what's going to happen now is the graph's going to get squashed down from here, and actually this point of intersection will be outside of this domain, will be bigger than a. If a is less than 1, that will be a number that's bigger than a, and so actually we're only going to be looking at this bit of area in here. Okay, and so we're still going to have our y equals the square root of x. This is y equals ax squared. So now what we find is they're still intersecting at a to the power of negative 2/3, but that is now something that's bigger than a. And so actually we're just looking at this bit of area in here. And so we want that area to be a third. So our area is going to be the integral from 0 to a of root x minus ax squared. And that has to equal a third. Let's see if we can edit this. Get rid of this whole second integral. And we only want to integrate up to a. Okay, and when we do that, again, this is when a is between 0 and 1, so we're not interested in that a equals 1 solution in this domain. So 2 decimal places, 0.77. Okay, so there are 3 possibilities. The one when a equals 1, the one when a is equal to 1.13, so it's bigger than 1, and the one when a is equal to 0.77, so it's smaller than 1. So let's just check we've answered the question. Find the values of a. Yep. So therefore we get a equals 0.77, a equals 1, or a equals 1.13. That's our 3 possible solutions. Okay, and we're up to question 3. Okay, so q of x is log e of x squared minus 1 minus log e of 1 minus x. So let's define that function. Q of x log e of x squared minus 1 minus log e of x minus 1. 1 minus x, sorry. Okay, state the maximal domain and range of q. Okay, so in terms of log functions, domain is to do with the fact that the thing inside the log has to be bigger than 0. So that means that x has to be less than 1 for that part of the function to exist. We also need x squared minus 1 to be bigger than 0. That's a quadratic inequality. X squared minus 1 is bigger than 0 when x is less than negative 1, or when x is bigger than 1. Okay, so we need the intersection of all of those things. So that is going to be x is less than negative 1. So let's just check if that makes sense looking at the graph over here. If we were to graph q of x, let me just get that window back to something normal. And we can indeed see it looks like the domain there is x less than negative 1. So domain of q is going to be from negative infinity to negative 1, and the range of q, we can see it's a log function and it's going to be r. Find the equation of the tangent to the graph of q when x equals -2. Some 1-mark question with a CAS, because it's a menu 4-9. Tangent to q of x when x is equal to -2 is -x minus 2. Now, equation of means it does need to have a y equals, so you need to understand the output that your CAS gives you, and therefore the equation of that tangent is y equals -x minus 2. They comment on that frequently in examiners' reports. -x minus 2 is not an equation, and so you wouldn't get any mark if there's no y equals. It's also not tangent equals, it's y equals. The equation of the tangent is y equals -x minus 2. Find the equation of the line that is perpendicular to the graph of q when x equals -2 and passes through the point -2, 2. Okay, so it needs to be perpendicular to this line that we've just found here, okay? But it's not the normal though, okay? So let's just be clear about, let me go back over to the graph here. So what we've just found is, let me draw the graph, get rid of this out of the way so we've got some space. Okay, so our function looks like this. That's -1. Therefore, -2 is going to be somewhere here. So we found the equation of the tangent at this point. I'm just going to actually draw it slightly differently. Okay, let me make it a bit steeper than that. Okay, so that's -1, 0. The tangent at -2 again, I need to recalibrate my pen, is there. Okay, and we found that's y equals -x minus 2. So therefore that's 0, -2. So the question here in part 2 says, find the equation for the line that is perpendicular to the graph of q when x equals -2. So it has to be perpendicular here, but doesn't have to be here. Okay, so it's going to have that gradient, but it needs to go through the point -2, 0, which is down over here. So it actually needs to go this way. It needs to be perpendicular here. Okay, so the gradient is perpendicular, and so the gradient of this is going to be 1, because perpendicular to -1, and it's going to have to go through that point at 0, -2. So it has a gradient of 1, and it goes through the point, sorry, not 0, -2. My apologies. It's not that at all. It goes through the point -2, 0. So it has to go through this point, but be perpendicular. Okay, so that's the line we want there. So it has to go through the point -2, 0. So we're going to have, I'm going to use y minus y1, so y minus 0 equals gradient times x minus x1. And so the equation is going to be y equals x plus 2. Alright. Let p of x be this. Okay, let's define p of x. Okay, so it is e to the -2x minus 2e to the -x plus 1. Explain why p is not a one-to-one function. Okay, so let's have a little look at p. Okay, so it's not a one-to-one function because it fails the horizontal line test. Passes the vertical line test, that makes it a function. So it's sort of doing this, and then it's going to asymptotes out this way, okay, where that's y equals 1. Okay, so what I'm going to do is I'm going to show that it fails a horizontal line test. So let's say, for example, if we solved p of x equals a half. So if I solve p of x equals a half, we get two values. Let me just get them as decimals. We get x is approximately negative 0.5 and 1.2. Okay, and so because we get two solutions, that's sort of by definition why it is not a one-to-one function. It's in fact a many-to-one function. So I need to make some kind of statement. So since there exists two x values, negative 0.5 and 1.2, for one y value, 1/2, p of x is a many-to-one function, not a one-to-one function. Okay, so making sure you're offering some kind of explanation. Explain, i.e. use some words. Parrot the language of what you're being asked to explain. We're being asked to explain why p is not a one-to-one function, and you'll see the conclusion of my sentence says not a one-to-one function. Okay, so don't be ambiguous about answering the question. So I've got a little graph there that sort of shows horizontal line test being failed. I've got a calculation that I can use to justify it. So since there exists two x values, and I've stated what those values are, negative 0.5 and 1.2 for one y value, 1/2, probably should have written x equals negative 0.5 and x equals and 1.2 for one y value, y equals 1/2. P of x is a many-to-one function, not a one-to-one function. Okay, find the gradient of the tangent to the graph of p at x equals a. Okay, gradient of the tangent is just gradient of the curve, so we just need p dash at a. And so we're going to differentiate. In fact, I like to define a derivative. I'm going to define, just in case we need to use it, derivative of p as being the derivative of p. And then it's really easy for me to just do derivative of p at a. Okay, so we get 2e to the negative a minus 2e to the negative 2a is the gradient of the tangent to the graph of p at x equals a. The diagram below shows parts of the graph of p and the line x plus 2. Y equals x plus 2. The line y equals x plus 2 and the tangent to the graph of p at x equals a intersect with an acute angle of theta between them. Okay, so tangent at x equals a, I mean we can draw a anywhere. Let's just draw an example tangent. Let's put a here just so the tangents, they're going to intersect somewhere where we can see them. Oh, I've made it almost perpendicular. Let me make it quite low down here, perhaps. Okay, so let's make that a. Okay, so that means that the gradient of that line is whatever we just found up there, 2e to the negative a, I can copy it off my CAS, 2e to the negative a minus 2e to the negative 2a. We know the gradient of that line is 1. We want the acute angle between them, acute angle of theta between them. Okay, so this one, there's two angles, this one and this one. I haven't drawn them particularly differently, but this one looks like it's the acute one. Okay, find the values of a for which that angle is 60. Give your answers correct to 2 decimal places. Okay, so let's think about a couple of things here. If we draw in a horizontal line here, okay, that angle between a horizontal line and a line with a gradient of 1 is 45 degrees, okay, which means that I need this angle to be 15 degrees if this has to be 60, okay. So that means, let's go down to here, that we need this angle here to be 15 degrees. Now, one of the problems I've got here, because of the way that I've drawn this, is that we're potentially going to have negative issues. So we know that generally speaking, if we draw a line, this angle here, we know that tan of theta equals the gradient of that line. Okay. If, however, the line is negative, then actually what you find is, and we call that theta, we find that tan of negative theta is equal to m. Okay. And m is something negative. So the answer that you get, if you do inverse tan of, if you do inverse tan of a negative gradient, you get a negative angle, is what I'm saying. So you need to be a bit careful here. So this is where m is negative. It's greater than 0. Where m is less than 0. Okay. And this is where m is bigger than 0. Okay. So you just need to be a bit careful. Or the other thing is that you take the modulus of your gradient. Okay, so what I'm going to say here is that we're going to use negative 15 degrees. So I'm actually going to essentially say that, yeah, so we're going to say tan of negative 15 degrees is equal to the gradient of that tangent. Okay, so we need tan of negative 15 degrees is equal to the gradient of the tangent, which is the derivative of p at a, which is this expression that we found up here. Okay, so when we solve that, I'm going to need to be in degrees because my angles are in degrees. So we're going to solve. We're going to do tan of, tan of negative 15 has to be equal to the derivative of p at a. I'm going to solve that for a. And we want it to two decimal places, so let's do Control Enter. So in that instance, a is going to be negative 0.11, and that makes sense given where I drew that tangent, that it's going to be negative. Now I think we also need to think about, so I've looked at the example where the acute angle happens horizontally. So what I mean by that is the tangents intersect in that way, so that angle forms the acute angle. I think we might also need to think separately about a situation where the tangents end up intersecting that way, or the lines end up intersecting that way, and so we have to think about that being the acute angle, because I think that's going to give us a different situation. So let me draw in a different tangent. Let's think about putting the tangent somewhere else. Okay, so let's imagine we drew the tangent kind of here. It's going to get crowded here, okay? But if we drew the tangent up here, now this angle in here is our 60-degree angle. Okay, that's the acute angle. And so the difference now is, if I still think about this, that being 45 degrees, now that angle there isn't 15 degrees anymore. That angle there, so that total angle is going to be 120. So that angle there has to be 75 degrees. So again, treating this down here as being negative 75. And so then I also need to think about tan of negative 75 degrees being equal to the derivative of a. Derivative at a, sorry. Derivative of p at a. Okay, so let's make this negative 75. Control Enter. Yeah, and we get a different solution. So a could be negative 0.67. Sorry, I lost my cas there. Okay, and so two different solutions happening there. 3 marks. I possibly need to show a bit more than that, but most of it was in that diagram construction. And so I guess maybe just one of these equations, tan of negative 15 degrees, or you could also do it with a different angle as well, with slightly different logic, equals the derivative of p at a. One of those equations perhaps, and then perhaps both, one for each of the solutions. I'm not sure exactly how that mark scheme would go. Okay, find the x-coordinate of the point of intersection between the line y equals x plus 2 and the graph of p, and hence find the bounded area by y equals x plus 2, the graph of p, the x-axis, both correct to 3 decimal places. Okay, let me tidy up my graph again so I can get rid of all my angles, see what we're talking about. Okay, so it's asking me to find the x-coordinate of this point of intersection, okay, which should be straightforward, we just solve them equal to each other. And hence, so we'll need that point to find the bounded area by the line, the graph of p, and the x-axis. Okay, so this is the area we're trying to find. So we're going to need to split that into two integrals. It will be a triangle, or we can integrate x plus 2 and separately need to integrate p of x. Okay, so let's find the point of intersection first. So we're going to need p of x equals x plus 2. Again, even talking about previously that this exam seems reasonably straightforward, even it instructing you to have to find this point first feels pretty generous. We're giving our final answer to 3 decimal places, so it's fine to have this rounded. I'm going to use it exactly in my CAS, but I would still, if I wasn't going to, I would definitely be writing more than 3 decimal places here. This is an interim step, so we want to make sure we've got enough accuracy when we go to find our integral and then round that thing to 3 decimal places. Okay, so the area that we want is going to be the integral from negative 2 up to that intercept that we've just found. Oops, negative. Of the line. Plus, we're going to need the integral from that point of intersection up to 0, which is the x-intercept of p of x. Don't forget your dx's. Oh, we want both to 3 decimal places. Okay, my apologies. I forgot that finding this point of intersection was actually a specific answer that we do want. So 3 decimal places, making sure that we just write 750, but we're absolutely going to use that value nice and exactly in our CAS. In fact, to make it easier for me to use that, I'm just going to copy it down here, get rid of the x equals, so it's easier to copy later on. Okay, so then our area, we're going to need shift plus, we can integrate from negative 2, oops, up to this value. So now that I got rid of the x equals, that makes it easier to do that. X plus 2 dx, and I know that's a triangle, but it's not a very nice triangle, so let's just do an integral. Shift plus, I'm going to need to now put this number in the bottom limit, so I'm going to need to do a control C, because if I hit enter it's going to go back into that top limit, which was the last place my cursor was. So control V to put it down there. I'm going to integrate up to 0, and this time we're integrating p of x with respect to x. Okay, and that total area, sorry, just get that cursor out of the way, is approximately 1.038, correct to 3 decimal places. Okay, question 4. A teacher coaches their school's table tennis team. The teacher has an adjustable ball machine and they use to help players practice. The speed measured in meters per second of the balls shot by the ball machine is normally distributed around a variable w. Okay, so w has been defined for us. We must use w, not x. The teacher sets the ball machine with a mean speed of 10 meters per second and a standard deviation of 0.8 meters per second. Determine the probability that w is greater than or equal to 11, correct to 3 decimal places. Okay, it's just a straight normal distribution question. It's a 1 mark. Everything's been defined for us. All the same, I still always define my variable. The variable is defined for me. The w is the speed in meters per second of the ball shot by the ball machine. But I'm just going to clarify my information that I need to be able to put in the CAS. And that is that it's a normal distribution, that the mean speed is 10, and that the standard deviation is 0.8, so the variance is 0.8 squared. Then we want the probability that w is greater than or equal to 11. Okay, so there's a summary of all the information that my CAS needs to know, that I need to know in order to be able to write down this answer to 3 decimal places. That is normal, mean, standard deviation, and greater than or equal to 1. Okay, so all of that information is key, and so therefore that needs to be communicated. This question could be a 2-mark question, and that information is part of it. Identifying that information is key. So menu 552, lower bound is 1, upper bound is infinity, 1 to infinity, mean is 10, standard deviation is 0.8. Oh, sorry, it's not 1, it's 11. Probability W is bigger than 11. It was such a big probability, it was essentially 1. Okay, there we go. 3 decimal places, so 0.105. 106, sorry, to 3 decimal places. Find the value of k in meters per second, which 80% of the ball speeds are below. Give your answer in meters per second. Okay, so we want probability that the ball speed is less than k has to be 80%. So that's an inverse normal, menu 553, sorry, inverse normal. The area, and it always has to be a cumulative area, so we need the inequality to be a less than or equal to, which it is in this case. So that's 0.8. Oh, my apologies, I accidentally got myself an extra toolbar there. Let's see if we do that. Okay, mean is 10, standard deviation 0.8. Okay, so that k value, and we want it correct to 1 decimal place, is 10.6. Okay, so what we've essentially done there is we've got our normal distribution, mean is 10, standard deviation is 0.8, and we want 80% to be less than k. Okay. And so that is 10.6. The teacher adjusts the height setting for the ball machine. The machine now shoots balls high above the tennis table. Unfortunately, with the new height setting, 8% of balls do not land on the table. Let p hat be the random variable representing the sample proportion of balls that do not land on the table in random samples of 25 balls. Okay, so this is p. That's the population proportion. P hat, so find the mean and standard deviation of p hat. Okay, so remembering we've got our formula sheet, and our formula sheet gives us our mean and standard deviation of p hat. The mean is just p, which we know, and the standard deviation we're going to use that formula for. So the mean value of p hat is p, so it's 0.08, and the standard deviation of p hat is the square root of p times 1 minus p over n. So in this case, that is the square root of 0.08 times 0.92 over n. We shot 25 balls. Square root of 0.08 times 0.92 over 25. It doesn't give me a rounding, so I'm going to need to give an exact answer there. Okay, so let's, instead of writing 0.08 and 0.92, let's write those as fractions. So 0.92 is the same as 92 on 100. 0.08 is the same as 8 on 100. That'll force my CAS to give me an exact answer, which is going to be root 46 on 125. Okay, so I think just 2 marks for the answers there. I suspect it would have been reasonably common that students gave a decimal value for the standard deviation. So again, making sure that you're reading the question carefully. If you're not told to round, as I said to my students recently, at no point should you ever find yourself in an assessment thinking, how many decimal places will I write this down to? That is never ever your decision to make. Either the question will have told you how many decimal places, or if it doesn't, then you need to give an exact value. Use the binomial distribution to find probability that p hat is greater than 0.1 correct to 3 decimal places. Okay, it shouldn't need to tell you to use the binomial distribution, but that's okay. Okay, so this is where we need to have an understanding between, we have 2 different variables here, p hat, which is not a binomially distributed variable, and let's say x, which is a binomially distributed variable. So if x is the number of balls that don't land on the table, okay, x is binomially distributed. X is a binomial variable. There's 25 balls, and the probability that a ball doesn't land on the table is 0.08. Okay. Then we have this other variable p hat, which is the proportion of balls that don't land on the table. Okay. And the connection between these two quantities is that p hat is the number of balls divided by 25. Okay. And so that means that x equals 25 times p hat. So if what we want to find is the probability that p hat is greater than 0.1, we need to convert that to being about x. So that is the probability that x is greater than 0.1 times 25, 2.5. Okay, and obviously binomial is a discrete thing, so greater than 2.5 means greater than or equal to 3. So now we're going to able to use our binomial distribution where x is greater than or equal to 3. So it's menu 55B for a binomial CDF. Number of trials is 25. Probability of success is 0.08. And lower bound is 3 and upper bound is 25. Okay, so that is 3 decimal places, 0.323. So there's a roughly 32% chance that more than 10% of the balls won't land on the table, which is equivalent to saying greater than or equal to 3 balls won't land on the table. Okay, the teacher can also adjust the spin setting on the ball machine. The spin, measured in revolutions per second, is a continuous random variable x with a probability density function. Find the maximum possible spin applied to the ball machine in revolutions per second. Okay, so the maximum possible spin, this is where we need to be careful here. This is a probability density function, so we're not finding the maximum value of this function. This function is some kind of, they're just two linear graphs. They're going to do something and something. I've made it up, okay? But essentially that's what we've got happening there. And so the maximum spin isn't this maximum height. This axis is a probability axis. This is about the spin. X is the spin, okay? So the random variable x is the spin. And so the maximum possible spin is that, 50. So maximum spin is 50, what are the units here? Revolutions per second. Find the median spin in revolutions per second. Okay, so now we need to work out where we get half the area from. Okay, so I'm just drawing a really rough sketch of that, but I'm going to get that a little bit more precisely. So when x equals 20, if I put 20 into that, I get 20 on 50, 500, sorry, which is 2 on 50, which is 1 on 25. And then if I also put 20 into that, I'm going to get, let me just work that out, 50 minus 20 on 750. Also 1 on 25, so they definitely meet. And then let's just check, yeah, when we put 50 into that, we'll get 0. Okay, so we definitely have a graph fairly similar to the rough one I drew. So let's go 10, 20, 30, 40, 50. They're going to meet at that point there. Let's try that again. So it's not symmetric, just be careful about that because 20 is not in the middle there. That's 1 on 25. Okay, so I'm just trying to work out under which part of the graph the median is going to lie. So that bit of area in there is going to be 20 times 1 on 25, which is 20 on 25, which is 4/5. Oh, no, sorry, it's half. Half times that because it's a triangle. So it's 10 on 25. Sorry, just doing half times base times height for that triangle. So that'll be 10 on 25, which will be 2/5. Okay, so this is 0.4 here, 2/5. Okay, which means that the 50th percentile is going to be the median, therefore is going to be somewhere a bit past here. Okay, so my median is going to be somewhere there. And I could either do that by saying that bit of area there has to be 0.5, or I could say that that bit of area there has to be 0.1. So however I decide to do it, let's just say that the integral from the median up to 50 of that second part of the function has to equal a half. That's one decimal place, so we can put 0.5 if we want. So if we solve that integral, solve shift plus integral from the median up to 50 of the second part of the function, so that is 50 minus x on 750. That has to equal 0.5 or half. Solve that for m. So give me nice exact values. Obviously we can see that the median has to be between 20 and 50, so it must be the 22.6. So the median is 22.6, and that's got units, revolutions per second. Find the standard deviation of the spin in revolutions per second, correct to one decimal place. Okay, so for the standard deviation we're going to need variance first, and to find variance first we're going to need expected value of x squared and expected value of x. Okay, so let's work out lots of things. So we're going to have expected value of x is the integral from 0 to 50 of f of x. Now the CAS used to be good at integrating piecewise functions, and I'm pretty sure it's not anymore, but let's try it because it's going to make things much quicker for us. So let's play around with this a bit. Let's define f of x as a piecewise function and see if the CAS can handle it. It's one area of the CAS functionality that's actually gone backwards with various software updates. So that's x on 500, and the domain for that is 0 less than or equal to x less than 20. And then this part is 50 minus x on 750. And that is for 20 less than or equal to x less than or equal to 50. Alright, let's see how we go. Sorry, and I haven't written down my expected value function correctly because it's not that. That integral should be 1. That's the probability density function total area. The expected value is going to be x times f of x. So let's see if it can handle it today. X times f of x, dx. Great. Okay, although you'll notice it has given me a decimal value and I didn't press Control Enter, and my original function was defined with everything in fractions and nice exact values. So it looks like if we needed this exactly, we'd probably need to split this up into two integrals. So to do that we would just integrate from 0 to 20 x times this part of the function plus the integral from 20 to 50 x times this part of the function. So we just do it as two separate integrals. But if we can do it as one, it's going to be much more efficient. Okay, and so this is 23.3 recurring, which we can probably write that as a fraction if we needed to. It's obviously 23 1/3. Okay, so then we need expected value of x squared, which is the integral from 0 to 50 of x squared times f of x. So I'm just going to edit this calculation I just did, change the x to x squared. Okay, so that's 650. Okay, so then we can work out the variance of x, which is going to be the expected value of x squared minus the expected value of x all squared. So that's 650 minus 23.3 recurring squared. Actually, that's not approximate because I wrote it as a recurring decimal. Alright, so we're going to need this number minus... Oh, look, actually that wasn't exact either, although I think it probably was. Yeah, it's interesting. It's coping with the piecewise function, but only by always writing things as decimals. Okay, so this is going to be 105.5 recurring, and so then the standard deviation of x is going to be the square root of the variance of x, so the square root of 105.5 recurring, and we need our answer to one decimal place, so square root of that is going to be 10.3. Okay, the teacher adjusts the spin setting so that the median spin becomes 30 revolutions per second. This will transform the original probability density function f to a new probability density function g, where g of x is equal to a times f of x on b. Okay, so we're doing it by dilations. Okay, so this is a dilation by a factor of a from the x-axis and a dilation by factor b from the y-axis. Okay, so let's have a look at our probability density function. I'm just gonna draw it again. Okay, so we've got what we know currently is that the median value is here at 22 point something. What was it? 22.6. Sorry. Okay, so it's kind of there. And what we want to do is change it so the median is 30. So we want to move, actually let me use a different colour. So the median is currently there. And we want to move it so that the median now is here. Okay, so that means what we need to do is dilate this function so that we're going to need to dilate it. The only way we can change the median is we can only dilate from the y-axis and from the x-axis. So the only way to make the median go from 22.6 to 30 is a dilation. Okay, so we need to dilate by that factor from the y-axis, so it times by b. Okay, so can only change the median using the dilation from the y-axis. Okay, so what we need to do is 22.6 times b has to give us 30. So b is going to have to be 30 over 22.6. I'm just going to get that nice exact median value we had up here though. It wasn't 22.6 exactly. Okay, so let's take that. In fact, let's get it exactly. So let me go back up and do the median calculation again, which was this one. Okay, let me check which one was which again. Okay, so we want that first one, which is, so the exact value of this was, sorry, I've lost track of it. So 50 minus 5 root 30. Okay, so let's use the exact number there. Okay, so 50 minus 5 root 30 times b has to equal 30. So b is going to be 30 divided by that. Okay, and so that's going to be 50 divided by, no, sorry, 30 divided by, let's try again. 30 divided by 50 minus 5 root 3. Okay, so that's approximately, what do we want? 2 decimal places. So 0.73, correct to 2 decimal places. Okay, but if we've dilated the graph by a factor of b from the y-axis to move the median, we've now also changed the area. Okay, so if we've done that, okay, to change the median, we've made the area bigger. Okay, so what we also need to now do is squash the graph down by this factor to keep the area to keep the area 1. Hang on, it doesn't make sense that b is less than 1 because we have to have dilated it away from the y-axis, so b has to be a positive number. Oh, I've typed in 5 root 3, not 5 root 30. Okay, so it's not 0.73, it's 1.33. Okay, so that sort of does make sense thing we need to always be thinking about. Something definitely didn't make sense here. Okay, so we have multiplied the area. If we've dilated it from the y-axis by a factor of b, we've multiplied the area by a factor of 1.33. Okay, and so therefore, to counteract that, okay, so to keep area at 1, total area equals 1, need to dilate by 1 on 1.33 from the y-axis, from the x-axis, sorry. Okay, so we're now going to need to, as I said, squash things down this way by a factor of 1 on 1.33. So 1 on that is 0.75. Okay, so that means that A is going to be 1 on 1.33, and so therefore that is 0.075. So if we dilate by a factor of 1.33 from the y-axis, we make the median 30, and then we need to dilate by a factor of 0.75 from the x-axis in order to keep the area at 1. Okay, and question 5, the final question on the exam. 10 marks, so about 15 minutes. I'm sure it will take longer than 15 minutes along with my explanation. Let's see how we go. Part of the graph of f, which is a sum of a sine and a cos function, is shown below. State the period of f. Okay, so we can probably attempt to see the period from the graph. So, you know, if we think about it starts here and it gets back to that point, there's a full period there, looks like it's 4 pi. But the other thing is to understand how the period works when we have sums or products of trig functions. And the period of this graph alone, period for that bit would be 2 pi on a half. So that graph has a period of 4 pi. And the period for this graph is 2 pi on 2, so this graph has a period of pi. But if you're adding those two graphs together, you're going to need the lowest common multiple of these two separate periods to get the period of the sum function. So the lowest common multiple is indeed going to be 4 pi, and that matches what we're seeing on the graph. Okay, so the period is going to be 4 pi, and that is the lowest common multiple of the period of the two separate graphs. State the maximum value of f, correct to 3 decimal places. Okay, so we're looking for that. It looks like it's probably 2, but it says 3 decimal places, so I'm sure it's not exactly 2. All right, so let's get this function defined so we can work with it. I'm just going to clear my variables and my cas. Okay, so defining f of x as being, I need to be in radians for this. We used degrees earlier in the paper, so just watch those kind of things when you're working with trig functions. So sine of x on 2 plus cos of 2x. Okay, so we could do a couple of things here. I mean, we can see that the maximum is happening at pi, so we could probably just do f of pi. It looks like it's 2, but, oh sorry, state the minimum value. Okay, so minimum, it looks like they're not quite on pi on 2. So, alright, sorry. Minimum value, so let's do perhaps function min. So we could use menu for 7. We could do function min for f of x. Now, it's going to give me a general solution because there's going to be infinitely many places where there's a function minimum. So let's just do it within one period. So given that x is between 0 and 4 pi, then we won't get infinitely many solutions. Okay, so that's where the function minimum happens. So it looks like it's finding this. It's interesting, it should have given me 2 solutions, I think. Perhaps they're not actually at the same height, those 2 points. I wonder if I just found a solution between 3 pi and 4 pi. So interesting. Okay, so they're although that minimum, yeah, okay, anyway, I'm overthinking it. So now we're just going to need to substitute, actually I'm going to keep that one, I just want to check it. We're going to need to substitute, I'm going to go with the first one, into f of x. So given that the line above has an x equals, it's easier to just type f of x given that, and then that lets me copy this rather than have to delete the x equals. Okay, so negative 1.722, I just want to see whether it is the same minimum value at that other, this value. Yeah, they are the same. It's interesting why function min with the domain from 0 to 4 pi didn't give me both x equals 7.938 and 10.912. Yeah, it's sometimes those sort of function mins can be a bit finicky, and this is a bit of a complex function, and so it actually hasn't given me all of the solutions in that domain when I used function min. If we'd solved our derivative equal to 0 over that domain, in fact, let's just check that. So I'm going to define a function. I'm going to define my derivative of f as being derivative of f. If I were to solve the derivative of f equal to 0 over that domain, actually it's going to give me more than this though. Because it's also going to give me the maximums when I do derivative. But that does give me all of the solutions. It gives me the 10.91, gives me 9.42, which is this one here. That's the 3 pi. It gives me the 7.93, which is this one. Okay, so it actually gives me all of the solutions where using function min didn't, and actually there's 2 x values, so it gives us the minimum. Anyway, regardless of that, they give us the same minimum. It's a 1 mark question. I'm just going to write that value down. So the minimum value of f is negative 1.722 to 3 decimal places. Okay, find the smallest positive value of h for which f of h minus x is equal to f of x. Okay, so f of h minus x is the same as f of negative x minus h. And if I know my transformations, that's a reflection in the x-axis, sorry, in y-axis, and then a translation to the right by h. Okay, so what I need to think through is, if I reflect the graph in the y-axis, how much do I then have to translate it to the right by to get it back to being the same graph that it was? Okay, so let's think about this. If we reflect the graph in the y-axis, we're going to have it going the other way, so it's going to be doing this bit here. I'm not going to get this graph shaped nicely, but etc. Okay, so reflecting the y-axis, and then the question is, then I have to translate it to the right by h to make it back to the same graph. So I'm going to have to translate it that far. So I'm going to have to translate this point back to this point, which means I'm going to have to translate it 2 pi to the right. Okay. Okay. So must translate right by 2 pi to return to original graph shape. and so that means that h is going to equal 2 pi. So obviously it was the smallest value of h, so it would also have been possible to translate to the right by 4 pi and produce the same graph. And again, I could do it by 6 pi or 8 pi, so the smallest value would be 2 pi. So again, that's just a graphical understanding of transformations. If you solved that, I don't think you'd be able to solve that to get a solution because there would be infinitely many solutions. If you just tried to solve f of h minus x equals f of x. So you really do need to be able to think through the transformations there. Okay, consider the set of functions of the form g a of x. Okay, so we're going to generalize this function. So up here we've looked at it where that a value is 2. Okay, so we've got 2's here, and now we're going to change them to a's. Okay, so what we would expect to happen is that the period of this, where it was 2 pi on a half, so it was 4 pi, is now going to become 2 pi on 1 on a, so it's going to be 2a pi, and the period of this bit would be 2 pi on a, and the lowest common multiple of those will be that, so that will be the period of the overall function. This value here will be 2a pi, this value here there will become a pi, this value here will become a pi on 2, this value here will become 3a pi on 2, etc. Okay, so that's essentially what we're doing. That's only going to change the period. It's not going to change anything to do with the amplitudes. Actually it might, because it's not just a straight dilation. Okay, let's not declare things we're not sure of yet. So state the value of a such that g a of x equals f of x. Okay, so that's us just noting that a would be 2. A equals 2 would give us f of x. Find an antiderivative of ga in terms of a. Okay, I'm going to define g of x. I'm just going to call it g of x in the CAS. Actually, let's use our definition for f and edit it. So let's make that a. Just checking that that a is not bold. I haven't used it for something else. I'm going to call this g. Okay, let's do an antiderivative of g of x with respect to x. Okay, so an antiderivative of g a of x with respect to x. So an antiderivative means we don't need to worry about the plus c. I'm going to write that as 1 on a sine of ax minus a cos of x on a. So that means no plus c. Use a definite integral to show that the area bounded by GA and the x-axis over the interval from 0 to 2a pi is equal above and below the x-axis for all values of a. Okay, I think we'll need to use more than a definite integral. I think we're going to need to use multiple definite integrals. Actually, no, we don't. In fact, that's a nice little hint to us that we don't need to use multiple definite integrals. If we have the same area above and below the x-axis, let's take a much simpler thing. If we did something like this, and we integrated from here to here, if we just integrate, let's say that's 2 and that's 1. If we integrated from 0 to 2, whatever that function is, that should equal 0 if this area here is the same as this area here. Okay, so as long as the integral from 0 to 2a pi is equal to 0, that would mean that we have the same amount of area above the x-axis as we have below the x-axis over that interval. Okay, so we just need to show that that total integral is 0. Okay, so we're going to need to integrate from 0 to 2a pi ga of x with respect to x. So that means integral from 0 to 2a pi of sine of x on a plus cos of ax dx. We've just worked out an antiderivative, so that means 1 on a sine of ax minus a cos of x on a from 0 to 2a pi. Okay, so let's sub in 2a pi. So we're going to have 1 on a sine of, if we put in 2a pi in place of x, we're going to have 2a squared pi minus a cos of, that will just be 2 pi because those a's will cancel out, minus 1 on a sine of 0 minus a cos of 0. Okay, so we have 1 on a sine of 2a squared pi. I might write that as 2 pi a squared. Just think that'll help me think a bit differently about it. Now, cos of 2 pi, cos is the x coordinate at 2 pi around here. The x coordinate is 1, so that's minus a. Then sine at 0, the y coordinate at 0 is 0, so that whole thing there is 0. And then we have minus minus, we're going to have plus a times cos at 0 is the x coordinate 0, that's 1. Okay, so we've got minus a and plus a, so they cancel out. And so all we have here is 1 on a sine of 2 pi a squared. Okay, so now we need to be able to think about this thing here. So we obviously need it to be equal to 0, but we can't just write that that equals 0. Okay, this is a show that question. We know that that area is going to have to be 0. And so we need to show how we know that that thing equals 0. And we do, we just have to break it down. Okay, so what do we know about a? A is a positive integer. Okay, even if it wasn't, I think we'd be okay in this case. It needs to be an integer though. Okay, so we know that a is a positive integer. So that means that a squared is also a positive integer. Okay. Which means that 2 pi a squared is a positive integer multiple of 2 pi. Which means that it is always going to be located there in the unit circle. Okay, and so sine is the y coordinate, and sine at that location in the unit circle is always going to be 0. Okay, so we know that sine of 2 pi k equals 0 when k is an element, when k is a positive integer, and so therefore sine of 2 pi a squared is equal to 0. Okay, and so the integral from 0 to 2a pi of ga of x dx is equal to 1 on a times sine of 2 pi a squared, which means it's equal to 1 on a, sorry, just lost a bit of lag there, 1 on a times 0, and therefore it's equal to 0. And then we know, because the total integral is 0, that must mean that we have the same amount of area above and below the x-axis. Therefore, since the integral from 0 to 2a pi of ga of x dx is equal to 0, there must be equal area above and below the x-axis. over the interval it's lagging, where x is an element of 0 to 2 pi a it was, or 2a pi. Just checking that was inclusive. Yep. So show that the area bounded by g of a and the x-axis over the interval is equal above and below the x-axis for all values of a. Yep, so regardless of the value of a, that integral will always equal 0. And so therefore we can make that conclusion. Okay, part F, explain why the maximum value of GA cannot be greater than 2 for all values of A, and why the minimum value of GA cannot be less than negative 2 for all values of A. Okay, this is really just about us thinking about the fact that this is a sum of two functions. Okay, so if we think about, sorry, my pen's stopped writing there. There we go. So GA of x is, let me just get the function again. So it's sine of x on A plus cos of AX. Okay, so if we break this down, the range of sine of x on A, it has an amplitude of 1, and so it's from -1 to 1. And the range of this is also from -1 to 1. Okay, which means that the maximum possible value we could get from GA of x is if we had the maximum value of sine of x on A added together with the maximum possible value of cos of AX, and that would be 1. Okay, and then the minimum possible value of GA would have to be where the two minimum values are added together, so -1 plus -1, and so therefore -2. And so we therefore know that the entire, the sum function has to have a maximum that is can't be greater than 2, and a minimum that can't be less than -2. Okay. So max possible value of GA is sum of, I feel like I need to call these two separate functions something different. Let me think about how I'm going to say this. Okay, so let me just give myself some space. Okay, so range of sine x on A and cos AX, range of both, is -1 to 1. Therefore, max value of GA cannot exceed maximum of sine x on A plus maximum of cos AX, which is 1 plus 1, which is 2. Minimum value of GA cannot be less than min sine x on A plus min cos AX, which means -1 plus -1, which is -2. So I think it's just some logic around that the range of each of those two separate functions, the minimum value of each of those is -1. And so therefore, if we're adding these two functions together, the lowest possible value we could ever get would be -1 plus -1, and so -2. Similarly, if the maximum value of each of those separate functions is positive 1, the maximum possible value we could get by adding these two functions together is positive 1 plus positive 1. Sort of thinking through that addition of ordinates process that happens when we add the functions together. Okay, final part of the question. Find the greatest possible minimum value of GA. Okay, this is a 1-mark question, so we just need to find this, and I'm not sure that there's a nicer way to do this other than to just explore what this graph looks like for different values of A. So I've got G to find. Let me go over to my graph. Oh, where have I got functions here? Just going to delete. Okay, let's sketch G of X here. Now it's got an A in it, so it'll ask me about a slider, and I do want a slider. Let's play with it. Okay, we talked about sliders earlier in this video, and they are not very fun. I'm going to minimize it. I find them much easier to use when they're minimized. I'm right-clicking, and on your handheld to right-click, you need to press Control menu. I'm just going to go to the settings. A has to be a positive integer, so I'm going to make the minimum value of A 1. And let's make that 10 so we can go a bit further. We just want to count up in ones because A has to be an integer. Okay. Alright, so that is what this function looks like when A is 1. I wonder if we need a bigger domain than that. I'm just going to menu for 1. Let's maybe just look at this from, oh no, let's do negative 8 pi to 8 pi or something like that. Okay, let's just play with it. Maybe let's make these a bit smaller. Okay, so we want the greatest minimum possible value of G. So therefore we want the minimum turning point of the graph to be as high up as it can be. Okay, so here it looks like it's about, what are these counting? They're counting in 0.5s. Let me make that 1 so we can see more clearly. Okay, looks like it's about like 1.2-ish or something. Alright, so when A is 2, that minimum value came down lower. So if we're looking where this minimum point is, it's definitely down lower there. Equals, oh sorry, I went the wrong way. So definitely the minimum value, comparing 1 to 2, the minimum value got lower. 3, that looks like it's even lower again. 4, that looks like it's even lower again. 5, 6, 7. Okay, so this minimum value is coming down here. It looks like it's getting closer and closer to 2 as we make A bigger. Going the wrong way, sorry. It's certainly not getting higher. So there's where A equals 10, A equals 9, A equals 8. Looking at the lowest point of this graph, and I want the lowest point of the graph to be as high as possible, the greatest possible minimum. Okay, so it looks like it's down around 2-ish. Still looks 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 down around 2-ish at the very lowest point. Okay, that's quite a bit above 2, and that's a lot above 2. Okay, so we can see from the graph by looking at graphs of GA for different values. Oops. For different values of A, we can see that the greatest minimum occurs when A equals 1. Okay, so that means when A equals 1, G1 of X is sine of X plus cos of X. And so we want the minimum value, so we want to actually find the greatest minimum, so we want to actually work out what this minimum value is. And so let's just do, let me go back over here. this function, each of these separate graphs has a period of 2 pi, so the period of this graph is 2 pi, so we can just look from 0 to 2 pi. So let's redefine g of x as being, actually, we could leave it at that, because that's actually going to be, see how when I clicked on that, A is bold, and that's because it's referencing this slider, and I've actually got A set to 1. So we can use this version here, we don't need to get rid of the A's out of it. So we can find menu for, let's just do function minimum perhaps, 7 of g of x, which has got a equals 1 in it, for x, and again it's trig, so we're going to need a domain. We've decided the period of this function is 0 to 2 pi, so let's just use that. Okay, so that's when x is 3.92. I'm intrigued that that hasn't given me an exact value. Have I got my CAS set to approximate mode? Force it into exact. I actually like auto, but I've never seen function min. Oh, there we go. Okay. I've never seen function min do decimals like that. Maybe function min always gives decimals. Maybe I needed to solve derivative over that domain. We did that earlier as well, didn't we? I need to define the derivative. Anyway, I think if we'd solved the derivative, we would definitely have got 5 pi on 4 without being in, with still being in auto mode. Okay, so greatest minimum occurs when a equals 1. Okay, so we've essentially solved the derivative of that equal to 0. Actually, let's do it. So I'm going to define the derivative of g as the derivative of g. Okay, and if we solved the derivative of g equal to 0 for x over 0 to 2 pi, it would give us x equals pi on 4, pi on 4 and 5 pi on 4, and minimum of g1 equals g1 at 5 pi on 4, which is negative root 2. So the maximum minimum, the greatest possible minimum value of GA is negative root 2, which is about negative 1.4. So we saw earlier that when a equals 2, the minimum value was, sorry, it's just glitching a bit, the minimum value was negative 1.7, and so this is obviously higher than that, so it is a greater minimum. Alright, and that's the last question of the 2021 exam 2.